Today we're going to talk about two of the most important reactions in organic chemistry, the Aldol reaction and a related reaction called the Claisen condensation. And these reactions are going to involve enolate ions that we talked about in the previous video. Okay, so what we said previously was that if you use sodium hydroxide, or if you use sodium methoxide, or if you use sodium ethoxide as a base, you're going to establish equilibrating conditions. And one thing that can happen is an aldehyde or a ketone can get converted into an aldol product, which contains an aldehyde and an alcohol, and thus why we call it aldol. Aldehyde and alcohol are present in the same molecule. Notice that this new aldehyde doesn't have anything at the alpha position, but it has a hydroxyl group at the beta position. So this is also sometimes called a beta hydroxyaldehyde. And if we count carbons, it might be clear what's happened in this reaction. So in the starting material, look, we have 2 carbons, but in the product we have 1, 2, 3, 4. So somehow 2 molecules of the aldehyde combined to form our aldol product in the Aldol reaction. So how is this happening? Well, the way this works is that you have your aldehyde, right? And this is kind of the simplest aldol reaction. And we said that the hydrogen at the alpha position is acidic. So whatever base that we use, if we're under equilibrating conditions, we can deprotonate that. So at any time in the reaction, what we have is some enolate ion and some aldehyde that's not deprotonated, right? This is an equilibrium where there's measurable concentrations of enolate and measurable concentrations of aldehyde. So what can happen is once the enolate is formed, it can see a molecule of aldehyde which hasn't been deprotonated yet. This is a nucleophile. This is an electrophile, right? Because this carbon is electrophilic, so the negatively charged carbon, the nucleophilic carbon, attacks the electrophilic carbon. We break our carbon-oxygen double bond, and it's very important, I think, to count carbons here. So these are our first 2 carbons, right? Carbon 2 attacked this carbon 1 and broke the carbon-oxygen double bond, and then that is still attached to a methyl to give this product. But since we have a protic solvent, in this case water, we can pick up a proton from our solvent, which gives us our final aldol product here, as shown. So the trick with the aldol reaction, right, is you're under equilibrating conditions. Not only that, there's an equilibrium between the aldol product and the aldehyde, right, because these, every step is a reversible equilibrium. The trick here for any aldol reaction is you want to identify your alpha carbon, because in one molecule, this is going to be your nucleophile. If we break this molecule in half, right, this was our nucleophile which attacked the alpha carbon, or which attacked the carbon-oxygen double bond of another aldehyde, right? So this was carbon 1 of one aldehyde, which was attacked by the alpha carbon, carbon 2 of an enolate. So you need to practice this quite a bit to get good at drawing the product of aldol reactions, keeping in mind that this carbon is going to attack this carbon in another molecule. But notice that, at least for aldehydes, the aldol product is more stable than the aldehyde, and thus the equilibrium favors the aldol product. Okay, what you'll also see is that if you run an aldol reaction and you heat it, instead of forming the aldol product, you will eliminate a molecule of water. You'll lose this hydrogen and this OH to give a carbon-carbon double bond, and this is called an alpha beta unsaturated aldehyde, right? Because now we have a double bond between the alpha and the beta carbons. This is an alpha beta unsaturated aldehyde. It's conjugated, so remember when we talked about conjugated alkenes, conjugation conveys a tremendous amount of stability on a molecule, so there's a thermodynamic driving force for this reaction, right, because we're forming a conjugated compound, and there's an entropic advantage because we're generating two molecules from one molecule. This is breaking into two pieces, so there's a tremendous free energy driving force. This is a spontaneous reaction, generally speaking, if we can increase the heat. And so generally one thing that you'll see is that an aldol reaction without heat would give this product. The same aldol reaction, if we heat it, will go all the way to the condensation product. The reason why this is called a condensation product is because we're generating a small molecule, usually water, which historically would condense on the inside of the flask as little beads of water inside of our reaction. And so as the water is formed, you can see it inside the reaction, which is why it's called a condensation reaction. Okay, so depending on how you choose your reaction conditions without heat, these two aldehydes will combine to give us our beta hydroxyaldehyde, otherwise known as our Aldol product, or the product of aldol addition. Whereas if we heat that same reaction, so let's say we had sodium hydroxide and water and heat, then we'll go all the way to the condensation product. This would just be sodium hydroxide, water, and keeping it at room temperature or cold. It would stop here, or we can force it all the way to the condensation product. So what's the mechanism of the aldol condensation? Well, we just showed you this mechanism is you get in your aldol reaction, and I'm not going to redraw it, you get here, right? So notice there's still hydrogens available at the alpha position that could get deprotonated, and we're under basic conditions. So the next thing that happens in the aldol condensation is we form another enolate. So a hydroxide ion removes that hydrogen to generate an enolate. And now what can happen is something that seems strange until we start to think about what's going on, right? We're under strongly basic conditions. So we already have lots of hydroxide ions floating around. So now what can happen is, because there's a tremendous amount of stability conveyed on the molecule when it becomes conjugated, we actually get an elimination reaction where this negative charge, that lone pair of electrons, becomes our alkene. We actually get hydroxide as a leaving group, which is rare. But the reason why is because of the stability associated with the product and the fact that we're not increasing the energy of the system. We already have hydroxide ions present. So we get this plus a hydroxide ion. So that's the mechanism of the condensation. First formation of the enolate, and then an E1 mechanism where the lone pair of electrons becomes the alkene and this guy leaves to form our condensation product. So the cool thing about aldol reactions of ketones, so we just said for an aldehyde, right, the aldol product is thermodynamically favored. For a ketone, though, remember, carbon-oxygen double bond of a ketone is stronger, so to break that is actually thermodynamically disfavored, right? So the aldol product is not favored for ketones, but if we heat the reaction, then we get this alpha-beta unsaturated carbonyl compound, so we increase the stability. So we can favor aldol condensation products of ketones. It's difficult to favor those products, the aldol products of ketones. Okay, the last thing that I want to talk about in terms of the aldol reaction is what we've talked about up to this point is the same aldehyde as the nucleophile and the electrophile, right? If you have two different aldehydes that you want to react with one another, it's called the crossed aldol. So let's say we had a 2-carbon aldehyde that we wanted to react with a 3-carbon aldehyde. The problem is that there's 4 different aldol products, right? Because you can have the 2-carbon aldehyde as the nucleophile and the electrophile. So here it's the nucleophile and the electrophile. You can have the 3-carbon aldehyde as the nucleophile and the electrophile, or you can have other combinations where you have 3-carbon nucleophile, 2-carbon electrophile, or 2-carbon nucleophile, 3-carbon electrophile. And notice that you get 4 different products. You get a mixture of 4 different products out of this reaction. So it's a complete mess. No one would ever do this crossed aldol reaction. But there are crossed aldol reactions that do work that we're going to talk about on the next slide. So one way that you can favor the crossed aldol product is choose one of your 2 partners as an aldehyde that doesn't have any alpha protons, right? So we can't deprotonate formaldehyde. It doesn't have any alpha protons. It doesn't have any alpha hydrogens. So we will only deprotonate this alpha position, which will then add to this carbon, and this oxygen will eventually get protonated to form only this product. Another common aldehyde which is used for crossed aldol reactions is benzaldehyde, right? Because right here this carbon's already making 4 bonds. There's no alpha hydrogens here, so we could react these 2 things with one another to get a single crossed aldol product. So this is a strategy for getting a single crossed aldol. Use one of your 2 aldehydes that has no alpha hydrogens on it. Okay, a better strategy, let's say we want to go back to the example that we used before, is generate your enolate under non-equilibrating conditions. So we start with our 2-carbon aldehyde. We react it with LDA to quantitatively form our enolate, which we then add to our electrophile. So now we've quantitatively generated our nucleophile, which we add to the electrophile, so that the nucleophile only adds to this electrophile. We're never deprotonating the 3-carbon aldehyde. We get this product, which we can then protonate to give our final product. So this is another strategy for doing a cross aldol, is stoichiometric or non-equilibrating conditions for generating your enolate and then adding that to a new electrophile. Another thing about the aldol reaction, the last thing that we're going to talk about for the aldol reaction is you can have dicarbonyl containing compounds, right? And these can form cyclic aldol condensation products. Students are very intimidated by these reactions, but they're actually relatively straightforward. What you want to do is identify all your alpha hydrogens. You have alpha hydrogens here, and here, and here, and here, but you're only going to form 5 or 6 membered rings, right? Because those are not particularly strained. So all you want to do is number this 1, 2, 3, 4, 5, 6. Keeping in mind that this alpha carbon could attack this carbon-oxygen double bond to give a 5-membered ring. But if we deprotonated here and attacked, we'd only form a 1, 2, 3-membered ring. Or if we deprotonated here, we'd form a 1, 2, 3-membered ring. This would be a 1, 2, 3, 4, 5-membered ring. That would be the same. So the way you want to think about a crossed aldol is that we deprotonate at one of these alpha positions. That attacks this carbon. We break the carbon-oxygen double bond. We eventually get elimination of water. So we have a 5-membered ring. So generally what I do is I just draw a 5-membered ring, because this carbon is now going to become bonded to this carbon. On carbon number 5, notice that we have this carbon, a CH3. At carbon number 5, we also had an OH. Carbon number 1 is this one, which is bonded to carbon number 2, which possess a carbon-oxygen double bond. So this would be our initial aldol product, right? But then we can eliminate water, and you always want to eliminate water in a way that gives you a conjugated double bond. So when we heat this reaction, we lose water, and we get the same product that's drawn over here, except it's just rotated a bit. So one strategy that helps me is to count carbons. and make sure that everything is connected to each other in a proper way. That's the intramolecular aldol reaction. The last thing that we're going to talk about in this video is a Claisen condensation, which is a close cousin of the aldol reaction. Notice that instead of using an aldehyde or a ketone, in the Claisen condensation we're just going to use an ester. We deprotonate that with a base, which generates an enolate ion, which can add to another ester. But instead of getting an aldol product, we get a beta keto ester, right? We have a ketone here and an ester here, and the ketone is at the beta carbon to our ester, so this is called a beta keto ester. How does this reaction work? Well, hopefully we have a pretty good sense of how this is working, right? We have an ester which has an alpha hydrogen, so I think we had ethoxide as our base. We deprotonate this guy to generate our enolate, so we have ETO. Right, we have our enolate. This is under equilibrating conditions, right? So we have concentration of ester and we have concentration of enolate. Our ester now is going to serve as our electrophile, and this enolate is going to be our nucleophile. So we come in here, we attack, we break the carbon-oxygen double bond to get our tetrahedral intermediate, which is going to look like this. And now remember the rule that if we can reform a carbon-oxygen double bond, we will. So we come back down, we kick that out. That gives us our beta keto ester. What you have to remember though is that now we've made something that's way more acidic than the ester that we started with, because now we have a dicarbonyl compound. So this undergoes an rapid acid-base reaction with the base that we have in solution to generate a new enolate, which just sits there until we add acid in step 2 of the reaction, which gives us back the beta keto ester that we get out of the Claisen reaction. If we go back one, notice that step 1 is formation of our deprotonated beta keto ester, but in order to get a neutrally charged compound, we have to add acid in step 2 to protonate this carbon in the last step. Cross Claisens can work, but again, what you want to do is choose either one ester partner that doesn't have any alpha hydrogens, or quantitatively form your enolate and then add that to a different ester. We can also do intramolecular Claisen reactions, just like we did intramolecular aldol reactions, keeping in mind, right, that this position is going to get deprotonated, so we're going to have to add acid in the last step in order to neutralize that compound. So to summarize, we just learned 2 really important reactions. The aldol reaction is favored with aldehydes at room temperature or lower. It's an equilibrium which favors the products. The condensation reaction gives us an even more stable product, and it leads to loss of a water molecule, and that only occurs if you heat the reaction. You can do crossed aldol reactions, but you need either one partner that lacks alpha hydrogens or non-equilibrating conditions, and we can do intramolecular aldol reactions, but only if we're forming 5 or 6 membered rings. The Claisen reaction is exactly the same as the aldol, except we have esters, which possess an internal leaving group. We can get beta keto ester products out of that, and the rules for the crossed aldol are the same in the crossed Claisen condensation.